All right, hello and welcome everyone. I'm Alex, your host for the AI Research Roundup, where we dive into the latest developments in artificial intelligence research. Today, we're looking at a paper titled USP Unified Self-Supervised Pre-Training for Image Generation and Understanding, which was published on March 8th, 2025. So, the core idea here is tackling the challenge of connecting diffusion models used for image generation with models used for image understanding. The paper proposes a framework called USP, which uses a special pre-training method in the latent space of a VAE to initialize diffusion models effectively. This helps improve both convergence speed and the quality of generated images. Okay, and speaking of the practical side, the authors have actually released their code. This image here shows their official GitHub repository for USP. You can see they've organized the code into pre-training and generation sections, and importantly, they provide links to download the fine-tuning weights, looks like via Hugging Face. The repository also includes some key results, like graphs showing that significantly faster convergence I mentioned earlier, and tables with performance metrics. So it's all there if you want to try it out yourself or dig deeper into the implementation. Okay, so to get a better picture of how this USP pre-training actually works, let's look at Figure 1. It shows the overall architecture. You see an input image on the left, which first goes through a VAE encoder to get a compressed latent representation. This representation is then split into patches. Now, here's the core self-supervised idea. Some of these patches are randomly masked out, shown as the gray squares. An encoder, a vision transformer, processes the remaining visible patches, and then a decoder attempts to reconstruct the ones that were masked. This whole process helps the encoder learn robust features, and importantly, after pre-training, only the encoder weights are kept to initialize downstream models for generation or understanding tasks. The decoder is just discarded. Okay, so we just saw how the USP pre-training works, and this table 2, gives us some concrete numbers on how well it performs for image generation compared to standard models like DIT. It's comparing performance using FID and IS scores. Remember, lower FID and higher IS are better, and you can see across different model sizes like DIT large or XL. The USP initialized models achieve significantly better scores with the same number of training steps. For example, look at DIT XL/2 at 400,000 steps. USP gets an FID below 10, while the standard version is almost 20. It really highlights that faster convergence and improved image quality we talked about. Okay, so we just saw the performance improvements for those different model sizes like base large and XL in Table 2. Well, this table here, Table 1, just gives us a quick look at the actual architectural settings for those models. You see it lists the number of layers, the attention heads, and the embedding dimensions for each size. So, naturally, as you go from base to large to XL, the models get bigger, more layers, more heads, larger dimensions. These are the specific vision transformer configurations that benefit from the USP initialization we've been discussing. Alright, so we've seen the performance numbers and the model sizes, like that DIT XL model. Well, Figure 2 here shows us some actual example images generated by that DIT XL/2 model, initialized using USP. These are 256 by 256 resolution. You can see a variety of pretty high-quality images, different animals, like frogs, dogs, cats, birds, even a panda. So, this gives us a nice visual confirmation of the strong quantitative results we saw in the tables, showing the kind of image quality USP helps achieve. Alright, so building on those results in the example images we just saw, Figure 3 here gives us a visual look at that convergence acceleration we've been talking about. It plots the FID score, remember lower is better, against the number of training steps. You can see lines for both DIT XL/2 and SID XL/2 models, comparing the standard versions with the ones initialized using USP, which are marked as, quote, hours. It's pretty clear the USP lines start lower and drop much faster, reaching better FID scores with far fewer training steps. The paper highlights this leads to over 11 times faster convergence for DIT, and even more, like 46 times faster for sit. And also, notice the purple and orange lines show that longer pre-training gives an additional boost. Okay, so we saw how USP speeds things up in Figure 3. Now, Table 3 here gives us a head-to-head comparison, pitting USP against other recent acceleration methods. Things like REPA and REALS for both DIT and SIT models. It's looking at the FID and IS scores after 400,000 training steps. You can see for DIT XL/2, USP gets an FID of 9.73, which is noticeably better than the other methods listed there, like REPA and EQVAE. And for SIT XL/2, USP achieves an FID of 7.38, again outperforming the competition. So this really shows USP isn't just faster. It also leads to better generation quality compared to these other acceleration approaches at this point in training. So besides beating other methods like REPA on performance, as we saw, Table 4 here really drives home the efficiency point. It shows the training cost in GPU days for the DIT XL/2 model to reach a target FID score around 9.5 or 9.6. You can see training from scratch costs 622 days, and REPA is estimated at over 1,900 days. But the USP approach, combining its pre-training and fine-tuning, gets there in only 98 GPU days total. So it's not just better, it's way cheaper computationally. Okay, so, wrapping things up, we've seen how USP provides this really effective unified pre-training approach. It successfully bridges image understanding and generation, leading to much faster convergence and better final image quality for diffusion models, all while being way more computationally efficient, as we just saw. This unification is really promising, potentially simplifying how we train these powerful models. Well, that's all for this week's AI Research Roundup. Thanks for tuning in. I'm your host, Alex.